Hi there, this episode is an audio rip of a YouTube video. If there are any references to the screen or to the video itself, then be sure to go over to YouTube and actually check out the video, which will be the same title as this podcast. Thanks. Right, let's go through the appendices. Just really for completeness, I'm not going to go into great amounts of detail because, to be honest, we've already covered the appendices as we've gone through the book when they're really needed. But we'll go through them, starting with the top one. Appendix number 1. This is British standards to which reference is made in this standard. It's plain and simple. Anytime a BS is used, or a BSEN is used, or even reference to a harmonised document, HD, the British standard is mentioned here with title of the standard and a reference point to where it is used in BS 7671. Do note, though, that BS 7671 isn't in the appendix. Shouldn't be a problem. It's written on the front of the book, but I have seen people looking for it now, which is a bit confusing. But yeah, any of the British standards mentioned, they are referenced here quite well for you. We've then got Appendix 2. Now, Appendix 2, statutory regulations or statutory regulations and associated memoranda. We peaked on this in part 1 for the scope, object, and fundamental principles. Reference the relationship. It came out with it and it said it itself is not a statutory document, the wine regulations. They will be recognised, though, in law by statutory documents, and these are the ones that have primary position for that. So it says there, in the UK, the following classes of installations are required to comply with the statutory regulations indicated below. The regulations listed represent the principal legal requirement. Information concerning these regulations may be obtained from the appropriate authority, also indicated below. So the regulations are commonly accepted as recognised as methods of compliance with these statutory regulations given here. So we have the ESQCR, the Electricity Safety, Quality and Continuity Regulations. We've mentioned them a few times with regards to distribution requirements. The most common reference to them in BS 767 is when the ESQCR prohibits the use of a pen conductor or a TNCS system for external metallic structural areas, things like caravans, mobile units and things like that. But yeah, ESQCR is used throughout the document. Building control, work activities, you've got electricity at work regulations. So there's a bit of information underneath about what can happen if you fail to comply and how the statutory regulations may use BS 7671. We then have Appendix 3, which was actually quite useful through the book. This is the time current characteristics of overcurrent protected devices and RCDs. It does give you a bit of information initially about measurement of earthful loop impedance. You've got there a formula. ZS is equal to UO times Cmin over IA. And then it gives you further on the ZS measured must be less than or equal to 0.8 times UO times Cmin over IA. This is information that used to be in Appendix 14, but now has been put into Appendix 3. If you're very familiar with the 70th edition, you may obviously have a question which asks you to verify the measured value of earthful loop impedance or determine the measured value of earthful loop impedance. And if you go looking for that in Appendix 14, it won't be there anymore. It's now here in Appendix 3. Without going into too much detail with it, the purpose of the 0.8 factor that we have given here under ZSM, and it does say the symbol of ZSM does say is the measured impedance, okay, at the most distance point of the relevant circuit. The reason we have this 0.8 factor is a general rule of thumb to consider the temperature variation. When we install a circuit or we install a new circuit or we commission a circuit, it's not under load. It's not under considerable temperature change. It's maybe installed in a wiring system surrounded by other conductors that, again, are not yet put into service. These conductors reach their limiting or operating temperatures when under load, when under sufficient power. when we install a brand new system and we do commissioning, we do tests on that, there's no load, there's no thermal effects occurring within the system. Therefore, the values of resistance are, according to the measurement, less than accurate. The impedances will appear lower than they will in actual events, because obviously under load, conductors will warm up, and as a conductor warms up, its impedance comes down because of the increased resistance that occurs with the clashing of atoms and the electrons flying through there. So it's the temperature coefficient, resistivity of a conductor, temperature changes. That's what that's all about. So when we come to values of earth loop impedance, a measured value has to be considered as 0.8 as a multiplier of the values given in Appendix 4. In Part 4. That's what that little formula there talks about. We then have disconnection times for our CDs. We have general and non-delay and delay S-type, their rating. And then we have the rated residual operating current column, which gives you the rating of the device, followed by a residual current column, which is the same. That's the times 1. So a 10 with 10, a 30 with 30, 100 with 100. And then the tripping time required. So times 1, you can see, is 300 milliseconds. This is for 61008 and 61009 RCDs. Not for the old 4293s. Those are 200 milliseconds. We then have a changing time column for 20, 60, 200, 600. So what's happened there is the rated residual operating current has doubled. So this is the time 2 column. And that's 150. And then we have a 5 times column, which is 40 milliseconds. And we see that with protection against electric shock as an additional protective measure. That's when we have to have that 40 millisecond time. So that gives us the RCD times. And then we have what we've been very familiar with as we've gone through the book, the time current characteristic curves, where we have a different curve for a different protected device. And with these tables, we can identify how much current a curve can take with regards to the current applied to it. So it shows us the devices, and it tells us the time along the left and how quickly they'll disconnect proportional to the current flowing through them. And it's been summarized in table form on the same pages, which is very useful. We've practiced this a little bit, but do have a little practice yourself. Do come up with some scenarios and do kind of refresh yourself on that. Then we have Appendix 4. Appendix 4 is titled Current Carrying Capacity and Voltage Drop of Cables. There's a bit more to it than that, because it also has the factors. It has the correction factors for ambient temperature, grouping, buried cables, depth of burial. So there's a lot more information in there than you may initially think if you just look at it from the title of the actual appendix itself. We used Appendix 4 quite a lot. It kind of is its own little design guide when you flick through it. It gives an introduction, the consideration of the parameters of the circuit, the ambient temperatures must be known. Yeah, we have there an average ambient air temperature of 30, a ground temperature of 20 degrees. It then considers soil thermal resistivity, grouping, methods, installations, E and F, different sizes, conductor variations, other calculations, and then in section 3, if it looks a lot more familiar, we have the relationship, and then we have the symbols IZ, IT, IB, IN, I2, and the rating factors there. And then there's information that gives you a bit of a background on that. It kind of summarizes most of the content from protection against overcurrent and the cable selection part in 523. So it repeats here about the 0.725 factor for 3036 devices. It repeats the 0.9 factor for cables buried in the ground at 20 degrees. And then starts to talk about how to determine the cable size. And it's got the formulas for single circuits, for group circuits, and overload protection is not required. We went through this whole process back in chapter 52. So then talks about that, goes through the rating factors. And then it has voltage drop, and it's got the tables of voltage drop on page 383, where we know that if it's on a public supply, we have a 3% and 5% maximum. So for lighting of 3%, and other uses of 5%, so 5% maximum is 11.5 volt, 3% 6.9 volt. Those are the maximum allowances of volt drop. Discussion of reference methods. We talked about the reference methods and how they affect cable's ability to give off heat under load. We had table 4A1, which told us very simply, what types of wiring can be on what types of wiring system. And then we had table 4A2, which was the big table with numerous different illustrations of different methods of wiring, a little description of them, and the actual reference method itself that we use within the cable calculation sequence. So that's fairly given. Then after the table 4A2, we have table 4B1, which is your ambient air temperature table. My chair is squeaking. Is so if you are tabbing in your book, you would probably be justified in tabbing this one as your CA factor for ambient temperature, be it air at 30 or ground at 20 below. So you could have a scenario given in your exam which refers to a cable in the ground or a cable in free air, and it will tell you, a temperature, and it will also tell you the type of cable, whether it be thermosetting or thermoplastic. With regards to buried, we also have table 4B3, the source thermal resistivity, table 4B4 with regards to the depth of burial. So if you're asking about a rating factor for a cable buried in the ground, you know that that's where you want to go. All of the rating factors are here with the exception of CI, which was back in chapter 52 for thermal insulation. But all the other factors are here. And you've got the grouping one, table 4C1, that's a very common one in exams. Okay, so the remaining of Appendix 4 is your cable current carrying capacities. Do be careful to clearly read the title of every table. Is it armoured or non-armoured? Is it single core or multi-core? Is it copper? Is it armoured? Sorry, is it copper or is it aluminium? So get all that information as well. And then once you've done that, you can identify the reference methods, and then single phase or three phase, and then you go down, you find the highest value that is representative of your tabulated value of IT, and the highest value becomes IZ. So you remember we calculated IT by having IN or IB over the rating factors that we selected according to the scenario, and then that IT we took into this back end of Appendix 4, found the right cable type that we're going to go with, found the right number that's above our IT, and that was our new IZ, and we found the cable size, but we must then check the volt drop, which is on the adjacent table, and we verify volt drop according to the maximums in the table. We did all that as a process in chapter 52. I'm happy to do another example if you feel that you need that. Okay, moving on then to Appendix 5. Appendix 5 is the classification of external influence. And you'll realise now how many pages you're turning. There's lots of reference. I said this right at the beginning of the introduction video. A lot of this book is reference to information you already know from the main structure of the book. Appendix 5. This is classification of external influence. Key thing here is, remember, there are three general categories, A, B, and C. Those are environment, utilization, and construction of buildings. Okay, I see very common a question which asks you which of the following is not a general category of external influence. And I think like wiring systems is a very common answer. So be aware of the three general categories: environment, utilization, construction of buildings. That's given there right at the introduction of the appendix. And then we have obviously a second letter relating to the nature of the external influence. And that's a lot easier to understand when you look at the concise list on the next page. So when you look at environments, you have A, that's environment, and then you have another letter after A, which represents the area of this environmental external influence. So be it an ambient temperature, AA, temperature and humidity, AB, altitude, AC, AD for water, AE for foreign bodies, etc., etc. And do remember, there are three columns of them. There's AF, AG, AH, AJ, AK, and then on the next column is AM, AN, AP, AQ, AR. There's three columns. A lot of people have trouble reading that table for some reason. You also have utilization, which is B, as another general category, with BA for capability, BB, BC for contact with Earth, BD for evacuation, and BE for materials. Yeah, this all makes sense, utilization of the building. and the buildings itself is C. So get some familiarity there. Do remember that after this table you have guidance on that. Yeah, do understand that. Common example question I remember seeing is which external influence, which ambient temperature is considered as normal, and it was AA 1, 2, 3, and 4, I think, and which is considered as normal. When you actually go to AA 1, 2, 3, and 4, which is on the next page, page 447, you can see AA1, AA2, and AA3. It recommends specially designed equipment or appropriate arrangements, whilst AA4 says normal. In certain cases, special precautions may be necessary. So the one considered as normal is AA4. So, do understand how they can use that. Okay, so you got a long list of guidance on all of the external influences, and it's all proportional to whatever scenario you are given. We then have Appendix 6. This is the model forms for certification reporting. And do remember, this isn't an inspection testing course. This is a regulations course, and so really all we need to understand is some parts of this, such as when we should use one certificate instead of the other. So an installation certificate would be for a new circuit, new installation, or a fuse board change kind of thing. When we should use a minor work cert, and there's a big debate on when we should use minor work certs because a lot of people have differences of opinion. Fundamentally, if you are changing the characteristics of the circuit in any way, shape, or form, it requires a minor work cert. Remember, we said this in chapter 41. If I take a B-type circuit breaker and I replace it with a C-type circuit breaker, whilst I've added no resistance and I've changed no load, I have changed the performance characteristics of the protective measure of automatic disconnection of supply. Because when I change a B to a C, I require twice the fault current, which means I now need halving the for loop impedance. And if I don't carry out a minor work cert to verify a measurement to conclude that the for loop impedance is still suitable for the changed protective device type, then I haven't verified that the electrical installation is safe. So something as simple as changing a protective device from a B to a C or a C to a D would require minor work cert because there is data that you need to report. Other things that will be in this appendix will be who signs what form, what signatures are required on the form, construction, design, construction, inspection and testing, not the person ordering the work. And you may get questions on coding, C1, C2, C3, FI. Those are given on the condition report. If you're unaware of what codes are for what, you really shouldn't have a problem with that, but they are given there at the bottom of page 474 on the condition report sample. Okay. Moving on from Appendix 6 then, we have Appendix 7, Harmonized Cable Core Colors. It's reference to the cable colors that are harmonized with older standards and new standards. We had a table of cable colors back in part 5, and we have colors referenced here. It's simple as that. If you need to identify a color marker, there are two places you can look at. Depending on what it's asking for, depending on where you are in your exam, you may be in part 5. If it's things like DC motors or things like that, it might be there that's more suitable. But if you need to come here, you need to come here. The information's here as well. 8. Current carrying capacity and voltage drop for busbar, trunking and power track systems. I don't think I've ever seen this really touched on in the exam. All I've ever really seen is mentioning the BS standards that apply to power track systems. You can find that in part 5, part 4, appendix 8 or appendix 1. So they're all over the place in this book. But it requires specific information from the power track system, and there's a little bit of math to play with. But we don't need to go into this level of depth in this case. Similar with appendix 9. Multiple source DC and other systems. It's just illustrations of different arrangements. It's like different earth arrangement drawings. You have a TNCS system there. A multiple source system when separate protective conductor and neutral conductor to current using equipment. So there's a separate conductor to them. A TN multiple source system with a protective conductor and no neutral throughout the system. So it's a TN system. An IT system, it's just different arrangements. There's no need to kind of explain them all. They kind of describe themselves in the titles. But if you do want a bit more information on any one of them in particular, do let me know. But they're fairly simple once you've studied them. Appendix 10, protection of conductors in parallel against overcurrents. In the case of BS 7671 and probably your typical level 3 inspection testing course, all we need to remember with regards to parallels is for installation of a parallel and for the current equivalence to share a parallel so that the amount of current on the two conductors in parallel are the same. They should be of the same resistivity, of the same size, and of the same length. So their overall impedance is the exact same value. If the impedance or the resistance of the conductor is the same value, then it will share the current equally. If we were to change the conductor from a copper to an aluminium, there's just different resistivity there, so there's going to be a different value of current in one against the other. When we go beyond that, and we actually do have varying conductors or varying sizes or whatever, we then have to apply a little further mathematical stuff to that, which we don't really need to cover in this course. But it does give you a bit of information about the difference in impedance between the parallel conductors, causes unequal current sharing, for example, greater than 10% difference. The design current and currents for overload protection for each conductor should be considered individually. We must verify individual overcurrent protection if we have varying levels of current in varying conductor sizes. So there's some examples there where you have a single overload device, where you have an overload device for each of them in parallel. So you can have a good study of that, but again, we could have talked about that for a while, done some designs on it, maybe a separate video on this if you want, but we don't really need that for the BS 7671 purpose. Yeah, that's all we need to cover on that one, really. Figure 10D is quite a nice one. It shows you how you have a protected device and the current and flow effect when you have a protected device operate. Appendixes 11 and 12 aren't used. They have been moved or cut out. They've basically been moved to Appendix 4 over time. We then have 13, which is methods for measuring insulation resistance impedance of floors and walls to earth for the protective conductor system. This is where you actually use like an earth-free location as a protective measure. To verify a location is earth-free, we must establish a value of insulation resistance within the fabric of the area. So it shows you the methods used to verify that. Appendix 14 is, it used to be about measured earth loop impedances. It's now been replaced with this waffle, determination of prospective fault current. It appears that they just want to talk about prospective fault current here for some reason. It says Regulation 434.1 requires the respective fault current to be determined at every relevant point of the installation. We said that's obviously where there's changes in conductor size or insertions of overcurrent protected devices and things like that. Relevant points are switchgear and protected devices that may have operate or possibly disconnect a fault current. The devices have to be able to withstand the fault current safely and protect downstream equipment from damage in the event of a fault. Okay, yeah. Fault currents can occur in the event of insulation failure between live conductors and between live conductors and earth. Blah, 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 blah. In three-phase installations, the highest protective fault occurs between simultaneous faults between all line conductors. This is because a simultaneous fault between line conductors will result in a higher value of voltage than a fault between one line conductor and earth, because the voltage is different. An approximation of the prospective fault current between line conductors can be determined by a measurement between line, conductor, and neutral multiplied by the square root of 3. Yeah, well, square root of 3 is 1.732 because of the way they are out of phase and stuff. Yeah, you could just do one phase to neutral and do it by square root of 3. 1.732 is fine. An approximation of the protective fault current due to a simultaneous short circuit between all line conductors is determined by measurement between line and neutral multiplied by 2. So if you have a potential fault between all line conductors together. In a single phase system, it's going to be the greater of either the fault current between the line and the neutral or the fault current between the line conductor and earth. I'll be honest, I don't know why this information wasn't just thrown into part 6, really, if they want to talk about the test. But they've got it here. Appendix 15 Ring and radial final circuit arrangements. Yeah, it just illustrates how ring and radials work, sizes, and how you can install smaller cables if they're fused or if they're going to loads that can't overload and things like that. Simple arrangements. It also gives you the square area with regards to ring final circuits. Tells you things like cookers and ovens with a rated power exceeding 2 kilowatt should have their own dedicated radial circuit. A lot of us are leaning towards the preference of radials, especially in domestics these days. You then have devices for protection against over voltage, which basically just kind of talks about SPDs for a little bit. First illustration is a method of connection of an SPD, and remember it should be right at the origin, especially if it's a type 1 SPD, type 1 or type 2. It shows you how it can be connected with the very first overcurrent protected device. You then have illustrations of TT systems with either type 1 or type 2 connections, CT1 and CT2. The key indicator there is their position with regards to where the RCD is. With one, the SPDs are installed after the RCD, and with the other, they're installed before the RCD. Then you have an IT system, and probably the most interesting drawing is figure 16A5, which shows you a TN CS system with 3 SPDs, and it kind of shows you where they should be laid out. And if you look at it carefully, you can see that the SPDs are 4, 7 and 8. 4, which is right near the source, is labelled as a type 1 because it should be near the origin. 7 is labelled as a type 2, which is near the distribution equipment. And then 8, which is type 2 or type 3, which is near the equipment itself. So, they break it down as you go through. And then we have energy efficiency, Appendix 17. Now, this is obviously the new one. To be honest, they pulled this out because there was a lot of discussion in DPC when it was in the draft, and a lot of people were saying BS 7671's fundamental principles is to ensure the protection of livestock, persons and property against the detrimental effects that working with electricity can occur. That's the intent of BS 7671, and there was a challenge as to why there should be the need to consider energy efficiency within its scope. And technically that's true. The fundamental principles do not require it. There should be a consideration for it, but it should not be an impact on design with regards to the need to comply with the fundamental principles. So there was enough challenge, and what they chose to then do was, okay, they retracted the Part 8, which is what it was going to be. And they've made it Appendix 17. But it was mainly just to kind of keep people happy for now, because if you actually look at the very top of it, 17.1 scope, it does say at the bottom of that bit, it is intended that this appendix will be developed into Part 8 in a future amendment. So you may as well consider it as Part 8 in Amendment 1 anyway. At which time this will be blown up and probably will be as the draft said it would be. And I did a series of videos on the draft, and I went into a bit of depth with the draft of Part 8. So, if you're interested in how that's going to be, go back there and look, because it probably won't change that much. But some of the things they're going to talk about: the availability of electrical energy and user decision. So energy efficient management should be so designed that it does not reduce electrical supply availability and or services or operation below the level desired by the user. So our determination or our intention to save energy shall not inhibit the requirements of the user. So with regards to things like, you go to these places that have light switches, and you hit the light switch, and then you go walk 10 feet away and the thing turns off automatically. Or you go to the toilet and you're sitting on the throne and that light turns off when you're halfway through doing your thing. That kind of thing inhibits the user. Methods to save energy shall not inhibit the user for normal use. We shouldn't start tiptoeing around or gallivanting around or changing our everyday activity for the sake of saving energy. So one of the things it does say there, the user of the electrical installation must be able to take the final decision over whether or not to operate a service at nominal value or optimized value, or not to operate it for a certain time. Design requirements and recommendations. The designer should take into account the following without losing the quality of service and the performance of the installations. We mustn't lose any performance or service quality. A load energy profile, whether active or passive. The availability of local generation. So obviously we're talking here about clean energies, it says there solar, wind generator, etc. A reduction of energy losses in the electrical installation, and a tariff structure offered by the supplier. Think about what we did years ago with tariff structures with off-peak systems for Economy 7, things like that. So we designed heating systems that would utilise an off-peak supply. Determination of the load profile. The main load demands within installation have to be determined. The loads, together with their durations of operation and or their estimate of the annual load consumption of the main load demands, should be identified. Voltage drop. Consideration will be given to limiting the voltage drop within installation to a level below that required by 525.202 to reduce energy losses in the wiring system. So lowering the voltage drop further. What we need to remember, especially with this kind of area, is when we say let's say we do a cable calculation, and we go IB, IN, IT, and we get IZ from CA, CI, CG, and we calculate that, I don't know, we can install this cable with a 6mm, and with regards to the method of installation and all the rating factors, we get a cable that can carry, I don't know, 37 amp. And our calculation said it needed to carry 38 amp with limiting temperature, so it's just there, just there. What this is going to suggest is we should actually just make it bigger anyway, to bring it away from that limit. It's suggesting sizing your cables and then just going one up, because if we go one up, the conductor is going to reach under potential demand or full demand. It's going to reach a much lower maximum limiting temperature. And if we lower limiting temperatures, we lower thermal losses. If we lower thermal losses, then we lower energy losses, because a thermal loss is an energy loss. And that's what this is going to push. They're going to start saying, size your cable up one more. Size your cable up one more for thermal loss, and size your cable up one more for voltage drop gain. Alright? Because all of that stuff is a loss of energy. It says that there, cross-sectional area of conductors. Increasing the cross-sectional area of a conductor will reduce the energy losses, but will increase initial installation costs. So you've got to divvy that up. The decision as to whether to do this should be made by assessing both the savings within a time scale and the additional costs due to the increased size. Practical constraints such as the size determinations will also affect the sizing of conductors. Similarly, if you're going to install lighting circuits and you have a 2.5 with regards to current volt drop, and you were to say, oh, well, with my consideration of energy efficiency, I think I'll put a 4mm in. Might cost another 40, 50 quid or so, but after a 25-year life, they just save that money probably, if you have a way of calculating that. You then try and connect a 4mm into a terminal in a light fitting. The termination's probably not there. So you need to make sure that there's a lot of thinking to take place at this point. Then there's mention of power factor correction. Reducing thermal losses with power factor correction. That's a good idea. We kind of do that now, don't we? Zonal determination. The installation will be divided into zones for the purpose of energy efficiency analysis. The zone represents a floor area in square meters or location where electricity is used. Usage within the zones and energy efficiency and load management. Then inputs from loads, sensors and forecasts. So, clever ways to manage and control it. It goes on and on and on. Energy sensors, data logging. Inputs from the supplies, energy availability and pricing, smart metering. The IT did do a guide on energy efficiency. I do have it somewhere. It's one of my it's on my to read again pile. So I need to see how it, if anything in this changes it. Motors and controls. Lighting is there. The Barry Center method's not in here, which is interesting. That may come back. We'll see. We won't really know what they until they actually. A lot of this is just wouldn't this be a good idea? That's currently what it's like. Some consideration should be taken to with this, but clients are already driven with regards to things like LEDs and stuff at the moment. That's a whole monopoly in itself. But that's where energy efficiency is. There's it's going to come in Amendment 1. I can guarantee that. If it doesn't, well, it's going to come in. But and after the appendices, you've just got some reference tables, really. But there's not a lot kind of to gain from this other than what we've just covered, really. So that's energy efficiency done. Well, with Appendix 17 done, we're done with this video. If you want me to go through anything in more detail, do ask. But this is all the detail you really need for the regulations itself as a training course. I will finish this video now, but what I'll probably do next will be a video which goes through the exam and goes through the questions. If I can type the questions up and get that done, I will. Alright, speak to you soon.